Hello everyone, I'm Zhijun. Glad to share our work everyone in SDN contributes. Photo localization with well-designed rules. We proposed a new approach for SDN photo localization whose target is to identify faulty switches. Our approach, named Voyager, using probing techniques and works with only one single and persistent reporter rule per switch. We achieve this by letting each reporter rule monitor a certain bit in test packets. In brief, our most contributions include a compact coloring algorithm and a custom maskable match field. The former is to minimize the required number of monitoring bits, and later offers a place for test headers of any length. For probe-based approaches in SDN, here is the basic framework. A test package is sent from the controller to execute one or more rules, and eventually be matched and sent back to the control plane by a pre-installed reporter rule. Then the new these rules can be identified in the controller side. Existing approaches focus on two ways, per rule and per pass. The per rule way sends a gravity test packet for each rule, typically malloc. It's easier to handle network dynamics, and the price suffers very high bandwidth. The per pass way is more efficient, typically SDN probe, one test packet for multiple rules. Therefore, it can greatly reduce the volume of test traffic. However, they are not good at handling dynamics. There are two more challenges that haven't been solved. The first, a test packet targeting a switch S must not match the reported run in S. Otherwise, the test packet will be sent back to the control plane before accessing the run test. Molecular solution is tagging switch. Each switch will claim a header for itself and install the reported run with every neighbor. That works, but at the price of multiple reported runs per switch. SDN probe deletes the reported runs before next test. That's not a good choice, wasting the control bandwidth and meanwhile making internal parallelizable. The second challenge is how to avoid the negative impact on target network. One of the most important things, non-test traffic shouldn't be bothered. For this purpose, malloc bans some files and disallows non-test packets using it. SDN probe less aggressive, uses exact matching reported rules, and just hope non-test packets won't match them. So could these changes be parallelizable and non-invasive be solved in a better way? We said yes. More than that, no bandwidth dynamic good things should be kept. We want them all. Our approach, Voyager, comes from a simple idea. Switch tagging could be done in a bit level rather than like malloc in an entire header level. Think about the information entropy. It's more than enough to distinguish a switch from others using exactly one bit, and that's easy to implement based on the masking mechanism. So that's all Voyager does. Install one single and persistent reporter rule in every switch with the highest priority, namely at the top of long-test rules. Each reporter rule monitors a certain bit of packet. For example, let's switch SI monitors S bit and report the packet with one SS bit. We call this simple assignment. Then, composing test packet is super easy. If the target includes SI, then set the S bit as 0. If not, set as 1. Even better, this idea can unify the program per pathway. The only difference is the target includes only one switch, or includes several switches in a path. As a routine, we define a two-round for localization scheme. In the first round, do the per path test. If the expected reporter doesn't report test packet in time, the test will be considered as failed. If so, a second round test will be triggered, where each rule in the path is tested using per rule test. Let's see an example. Here is a topology with 6 switches. Now we want to test a path S1, S2, and S3. With simple assignment, the test packet will be composed like this. Let the first, second, and third bit be 0. This will silence all targets. Then let the first, fifth, and sixth bits be 1. This will activate all reporters, including the expected reporter S4 and the unexpected one S5 and S6. These unexpected reporters are very helpful, especially in the detail case. They regulate the test packet's route and ensure any deviation from the expected path will be reported. Now, compact coloring, Voyager's assignment algorithm. Its motivation is a simple assignment requires as many bits as the number of switches. It's simple but low enough. We want a more efficient assignment algorithm. So if we treat the monitoring bits as colors, then the assignment becomes a Renex rotate coloring problem. The Renex thing comes from such a fact that one bit is enough to distinguish two switches. Shannon gives a hand again. Two switches, even if they cannot monitor the very same value as very same bit, they stand a chance of sharing the bit with opposite values, one for 0 and the other for 1. We use two switch graphs to describe our observations. First, if and only if one is a reporter of the other, these two switches cannot monitor the same value at the same bit. That's what G alpha describes. Second, if and only if both switches are targets or reporters in a test, they cannot share monitoring bit with opposite values. That's what G beta describes. Then we do the greedy coloring on G alpha and relax it based on G beta. The relax part is somewhat tricky. To put it simply, we coloring the current switch. The greedy coloring will always choose the minimum color different from all labels. However, due to the chance of sharing, compare coloring also considers color that has assigned to a neighbor. If it's shareable, that in the current switch and the color label do not have a corresponding edge in each beta. Besides compare coloring, we develop a custom match field to settle the test headers. This decoupling from standard protocols provides only three good things. First, making wager non-invasive. Because non-test packets will not have this field, they will never match any reported rule. Second, compatibility to existing approaches. Most of them focus on packet header generation, that's standard header, of course, and requires some certain headers to exercise rules. A custom field will never conflict with these solutions. Third, custom fields are easier to extend. The capacity can be designed based on the network scale. On the other hand, the support to custom multiple fields is good. For example, OpenFlow has the experimental extensions to do such things, which is supported by the hardware OpenFlow switches in most cases. The evaluation. The dataset is the internet topology view, and we can say on average 16 bits and at most 70 are required by our compare coloring. The maximum happens in the biggest topology, which has about 700 switches. Also, have we mentioned the threshold? It's for the path length controlling. Once the path set is identified by solving the path cover problem, the passes on test will be split under the path length threshold before building the switch graphs. That's a trade-off for reducing the required number of bits against the number of paths on the test. Of course, the threshold can be set at infinity, then no passes will be split. This result is just in this case. That's the impact of the threshold. Lower threshold, fewer monitoring bits. The price is more paths on the test. The operator can do this trade-off a lot if the number of monitoring bits are acceptable. The efficiency. We evaluate this on 5 topologies of different scales. Compare coloring as a variant of graded coloring. It's done in a single linear time scheme. The loads are switches, so it doesn't matter how many rules are there. It takes only tens to hundreds of milliseconds. That's negligible compared with the time for path cover solving, which is several seconds typically. The efficiency of localization is amazing, much faster than SDN probe. That's because at most 2 rounds of fully parallel tests are required in Voyager. And another reason, in Voyager, the localization is totally transparent to switches. This is nothing but packets and nothing but S0, and can be so focused on the low-level packet processing. They are designed for this. Conclusion. Our approach for SDN fault localization can work with one single and persistent reporter report switch. No bandwidth, dynamic, parallelizable, and non-invasive. A compare coloring algorithm and a custom match field is introduced. The code thing can be found on GitHub. That's all. Thank you.